Lithography is the method by which complex circuit patterns are etched into silicon wafers, which power all of our modern computers. Advances in lithography drive advances in computing power, which is why it is an industry valued at $592.8 billion as of 2022. ASML is a leader in semiconductor lithography, where they use extreme ultraviolet light to create the world's most advanced computer chips. To produce extreme ultraviolet light, droplets of tin are vaporized by a CO2 laser. The timing of this process is absolutely critical. If we know the droplet position to a high degree of accuracy and precision, we waste less tin due to mistiming of the laser. As a result, more wafers can be created in less time, which is one of the main goals of our sponsor. This is the purpose of the laser diode-based metrology module, to detect droplets with a high degree of temporal accuracy, and then to send an external trigger which could be used to fire the laser. Our project utilizes small water droplets as a safer stand-in for molten tin, and we are not activating an actual CO2 laser, but this project serves as a proof of concept that such an addition would be advantageous to add to a real lithography system.
The first and most challenging issue proved to be the generation of water droplets at such a scale. We did a literature search and discovered that others have asked and answered this question before. We decided to base our design off of an idea published by Daniel Harris, an engineering professor from Brown University. This concept uses a piezoelectric buzzer to perturb the surface of water in a reservoir, which is then dispensed using a high-precision nozzle with a diameter of less than 1 millimeter. The main reservoir is connected through tubing to a secondary reservoir at a different height. This creates a pressure differential. This results in a hydrostatic system with surface tension pushing upward and differential pressure pushing downward. When the piezoelectric diaphragm is activated, the balance is disrupted and a droplet is dispensed. We can trigger this buzzer by using a microcontroller. In our case, we decided to program a Raspberry Pi to send the signal.
We also needed a method to detect the droplets once they've been dispensed. This is where the laser diode comes into play. In a preliminary design, we saw that we had two basic options for detection. Either we could detect laser light reflected off the water surface, or we could detect the shadow that the water droplet casts when it enters the laser line. Both methods would be an accurate way of determining the water droplet's position, and both would require a laser and an optical detector setup. We decided to go with a transmission-based design. However, the optical design was not complete. We knew that there would inevitably be vibrations in our system that could affect the trajectory of the water droplet as it fell. This could cause the droplet to miss the laser beam if it fell to either side of the beam. As a result, we incorporated what is known as an anamorphic prism pair into the design. This allows us to squish the laser line from a circular shape into an elliptical shape, so that the water droplet is still only passing through 1 millimeter of light in the vertical direction, but we greatly decrease the probability that it will miss the laser beam entirely.
When a droplet passes into the beam, we see the optical signal drop on the photodiode due to the shadow of the droplet landing on the sensor. We built an electrical comparator circuit to read this drop in output voltage and signal to the computer system that a droplet has been detected. Using an op-amp comparator chip, we set a threshold voltage. When the photodiode output dips below this threshold, it sends a logic high signal to one of the Pi's input-output ports. It also sends a signal that lights up the indication monitor light.
The detector that we chose was a commercially available silicon photodiode with built-in amplification at 9 different gain settings. This detector has good efficiency in visible wavelengths and easily detects the laser beam. It interfaces easily with our electronic and software subsystems.
Because the system is so light sensitive, it is imperative that none of the components, especially the water droplet and the detector, are exposed to outside light. We came up with a cheap and creative way of ensuring our system was both light tight and accessible for demonstration and for maintenance. Using commercially available side table as the frame, we 3D printed brackets and slid textured ABS plastic panels into each side of the frame. It's simple, convenient, budget-friendly, and effectively blocks all stray light from entering our system.
While the system is dispensing and detecting droplets, all that information is being documented by the system's computer. We're running all the software and storing all data on a Raspberry Pi 4B microprocessor. The microprocessor reads the signal from the comparator circuit. When it reads that the comparator is sending a logic high signal to indicate that a detection has occurred, the software does a few things. First, it timestamps the detection so that the system can be sure exactly when it occurred. Then, it adds the index of the detection as well as its timestamp to a file, which is saved to the Pi's SD card at the end of the run so that all detections are indexed and logged. Additionally, it takes this timestamp information and uses it to update a plot that's displayed on the screen to the user. This shows the user that a detection has occurred. When the system is working properly, the detections are occurring at regular intervals, so this plot is a visual way of ensuring that everything is working smoothly.
The LDBMM has weight and size constraints provided by the sponsor, which we adhered to throughout the entire design project. Additionally, we have to operate entirely off of standard US American wall socket power. So we designed all of the electronics to be compatible with this exact format.
Our most important performance metric is the accuracy of the system. When a droplet is dispensed, are we detecting it? Our system requirement is that we should be able to detect droplets with 95% accuracy, but ideally we should perform better than that. To test this accuracy requirement, we have to run the system at 1 Hz for 1 minute. This means that 60 droplets should have been dispensed. Then, by checking the log that the software has saved to the SD card, we can determine how accurate the system was by looking at the fraction of the 60 droplets that we actually did detect.
Another important test that we executed was to ensure that the droplets were of the correct size. The droplets of molten tin that are being vaporized in the actual lithography system are very, very small. So it is imperative that our droplets are about the same size. The size is determined by the voltage at which the piezo operates, as well as the pressure differential between the reservoirs. Using a slow motion video and a background with a known spatial frequency pattern printed on it, we were able to determine that our droplets did fall within the 1 millimeter requirement.
The third crucial test is to ensure that the droplets are being dispensed at a constant frequency. It is essential that the system is consistent. We tested our frequency and frequency variance by again using a slow motion video setup. By visualizing the exact moment that the droplet exits the nozzle and noting the number of frames between droplets, we calculated the droplet-to-droplet frequency. We designed the system to run at 1 Hz, and it successfully dispenses droplets at that frequency with a variance of less than 10% over the whole run.
Our other requirements included having a latency of less than 250 milliseconds between the time the droplet enters the laser line and when the indication monitor light illuminates. We originally encountered issues of high latency, but we were able to solve these issues by directly wiring the monitor light in with our comparator circuit and not using the Pi as the trigger. As a result, the latency is entirely dependent on the electronic latency.
At the end of the day, our deliverables for this project are the following. First and foremost, we're supplying our sponsor ASML with a physical laser diode-based metrology module. This includes all of the hardware we've built, all the electronics we've assembled, the microprocessor with all the necessary computer code, and the frame that holds it all together. On top of that, we are providing a full CAD model of the assembly and part drawings for all our custom printed components. We are also including a ray trace model of the optical subsystem, a complete software package, and user's manual, and a set of example data from a successful 10-minute run of the system. With all these deliverables, we anticipate that our sponsor will have all the necessary documentation to implement the system.